Hello, pre-calculus students. We're going to continue right along here with complex zeros of polynomials, and in this video we're going to talk about the complex conjugate theorem. And this says a polynomial in standard form with all real coefficients should we say given a polynomial in standard form with all real coefficients if a complex number, and we'll just call it a plus bi, is a 0, then its conjugate is also a 0. Okay. So what this means is, like, if you have some sort of function, let's say if you have some sort of function f of x, and like 2 plus I, let's do a quick side example here. Some function f of x, 2 plus I is a 0, then 2 minus I is also a 0. Okay. The reason for that is this key word here, this key term here, real coefficients. Whenever you have real coefficients and you have something complex in there, the complex conjugate has to also be in there. Otherwise, it won't be real. Let me refer you back to the previous example. If you have a complex conjugate and you multiply it, if you have a complex number and you multiply it by its complex conjugate, you always get a real number. So that means if one of these numbers is a 0, then the other part of it is also a 0, because otherwise you're not gonna be able to get a real number. Okay? And you can kind of see from our previous examples back here, 2 plus 3i over 7 is a 0. And all of these numbers here are real coefficients. So then you know that 2 minus square root of 3i over 7 is also a 0. And these two are complex conjugates. They go in pairs, because two complex conjugates will cancel each other and leave you with a real number. So whenever you see all real coefficients, either all of the zeros are real, or you're going to have a complex conjugate and a complex number and a complex conjugate as the zeros. And so I'm going to pause this video right here, and then I'm going to flip the page over, and we're going to look at an example of how this applies. Okay. So this problem says 1 minus 2i is a 0 of f of x equals 4x to the 4th plus 17x squared plus 14x plus 65. Find all the other zeros and write in linear factored form. Okay. So if this is a 0, okay, all of these, you can see all of these are real coefficients. So we know that 1 plus 2i is a 0. And I'm going to refer here to the complex conjugate theorem. If a complex number is a 0 and you have all real coefficients, the conjugate has to also be a 0. Now, so that shows us that, we got one other 0, but we need to find all the other ones too. Maybe there's 2 or 3 zeros in here. And so to do that, we're going to start out by doing synthetic division. And it's going to seem a little bit weird here that we're doing synthetic division with complex numbers, but same rules apply. There's nothing wrong with doing this. So this is x to the 4th. Remember, I don't have an x to the 3rd, so I have to write in the placeholder here 0x to the 3rd, 17x squared, 14x, and then 65. And then I'm going to just apply the same rules. 4, bringing this down. 4 times 1 minus 2i gives you 4 minus 8i. 0 plus that gives you 4 minus 8i. And now it gets quite tedious. 4 minus 8i times 1 minus 2i. You can do it by hand, it's good practice, but for this problem, just because there's so many places where we can make an error, I'm going to use a graphing calc on my TI-83 to help me do this. So if you have your TI-83 with you, you can type in a complex number the following way. You can hit, so I'm going to type in 1, make sure you use the parenthesis, 1 minus 2, whoops, 1 minus 2, and then the I key is the decimal point. So hit second, and then hit the decimal point, and you can see the I there written in yellow, and that's going to show up on my screen. Okay, so I can do 1 minus 2i times 4 minus 8i. And it gives me negative 12 minus 16i. Negative 12 minus 16i. I should have written this out a little bit, more space here, but we can still do this. We add it, so we add the real components, 17 plus negative 12, that's 15, and then negative 16i comes along. And then we're going to do 1 minus 2i times 15 minus 16i. Gives me negative 17 minus 46i. When I add this down, this is going to give me negative 3 minus 46i. And then I'm going to multiply negative 3 times negative 46i times 1 minus 2i. And now this gives me a remainder, which I know is not correct, and I think I see my problem here. See right here. 17 minus 12i should be 5, not 15. Apologize for that. So I'm going to have to redo that part again. So in this time, from here I'm doing 1 minus 2i times 5 minus 16i. That gives me negative 27 minus 26i. When I add these two together, 14 minus 27, that's going to give me negative 13 minus 26i. I apologize for that. Then I'm going to do that multiplication, 1 minus 2i times 13 minus 26i, and this time it should give me negative 13. Yeah, it should give me whoops, whoa. Should be negative 13. Should give me negative 65 up here, and that leaves me a remainder of 0. Okay. Now, you see here, this intermediate step is pretty much useless, except that it helps me get to the next one. I don't want to use this at all because I got all these imaginary numbers all over the place. So what I'm going to do here, I'm just going to rewrite this. This is 4 minus 8i, 5 minus 16i, negative 13 minus 26i. And learning from my lesson last time, I'm going to give myself a little bit more space to work with here. Okay, so what I'm going to do next is, just like what we do with real numbers, once you know one of the roots, you divide it by that. I have another complex conjugate here, so I'm going to do that division again, and this time this should make things a lot simpler for me. So let's go through the step. First, I'm going to bring down the 4, then multiply. I'm going to get 4 plus 8i. And you can see here the imaginary terms are going to cancel, and it's just going to leave me with 8. 8 times 1 plus 2i is 8 plus 16i. And then these imaginary terms are going to cancel, leaving me with 13. 13 times 1 plus 2i gives me negative 13, I'm sorry, positive 13 plus 26i, and this is 0, which is my remainder. So just to bear in mind what this means here, we started out with x to the 4th, and we've done synthetic division twice, so these powers should be 2 lower, x squared, x, and then this is x to the 0th. Okay. And then I'm going to factor this, 4x squared plus 8x plus 13, using whatever method that you want to use. I prefer to use the quadratic formula in this particular instance, just mostly because I'm running out of space here. So opposite of b, plus or minus square root b squared is 16 minus 4 times, no, b squared is 64, excuse me, times 4 times a, which is 4, and then times c, which is 13, all of it divided by 2 times a, which is 4. Once I get all of that done, it comes out to negative 8 plus or minus the square root of negative 144 divided by 8. Square root of negative 144 is just 12i, so this is negative 8 plus or minus 12i over 8, and that simplifies to negative 1 plus or minus 12 over 8 is 3/2 I. So these are my zeros here. This is a 0 that was given to us. This is a 0, which is just a complex conjugate, and these are the other zeros that we found by factoring the quadratic. Okay? And so these are the 4 zeros, and we can write it in linear factored form, and this is not going to be pretty either. This is going to be x minus 1 plus 2i times x minus 1 minus 2i times x minus negative 1 plus 3/2 I times x minus negative 1 minus 3/2 I. And then we can distribute all of these little negative signs here. You get x minus 1 minus 2i, x minus 1 plus 2i, x plus 1, distributing this negative sign, minus 3/2 I, x plus 1 plus 3/2 I. And so this is the complete linear factored form. Okay. Now, let's recap a little bit here and look at this in the big picture of things. We have this statement here, and we want to know, is there a way for us to break this down further, to break it down into its most basic form, which is the factored form? And it turns out there is a way to do this if you're given one number to try. Okay? And the result that you get may not be a real solution. It might be complex. This is the most extreme case where all of the solutions here are complex. But the point is that given any higher order polynomial, there is a way for us to break it down into something that is at its most basic form. It may not look pretty, it may be a little bit messy, it requires a lot of tedious work, but it is a possible way, and it can be done. I mean, you won't be asked to do this too often in your life, but it's important that you have a basic understanding of where these concepts come from, so that it's not just some magic formula, and it's not just some magical graph. In fact, a graph would not work in this particular case. Okay. So thank you for watching. Have a wonderful day or a wonderful evening, and keep working at this. This is not easy, but it's also not entirely difficult. It's just following some of the basic steps and being careful and methodical in your approach.